Welcome back to ME 760 Engineering Analysis 1. So last time we started looking at the normal matrices and the eigenvectors for normal matrices and how to get or calculate those eigenvectors. And we concluded the last lecture by just getting some properties for a n by n general matrix are not a orthogonal or normal matrices. So let's continue this business and talk about simultaneous eigenvectors. So this will be the topics of this lecture. So the first thing we will ask a question and see how we can answer. So what do 2 n by n, or when do 2 n by n normal matrices, so if we have two normal matrices and each one of them is n by n, let's say A and B. When those two matrices will have the same eigenvectors, same eigenvectors. So this is a question. So let's look for the question right now, and this question will have two parts. To answer this question, we will have two parts. So the matrix A, the eigenvalue equation is just A operated on X I, and Xi is just the eigenvectors of matrix A, where Xi are the eigenvectors of matrix A. So those are the eigenvectors, and I goes from 1 all the way up to n. So there are two parts to answer these questions. So we will assume that all the eigenvalues, lambda i's, are distinct. Then the first part, we will suppose A and B commute with each other. So we can write the relation AB operated on the eigenvector Xi is nothing more than BA because of the commutation property. So the first part is we will assume that the matrix A and matrix B commute with each other. So we can write AB operated in eigenvector Xi equal to BA operated on Xi. Then what's AXI from here? So it's B lambda Xi. Then I can take lambda outside, and this will be lambda I multiplied by B Xi. So what does it mean now? It means that A, I can write it like this, A Bxi equal to lambda I Bxi. What does it mean, this equation? This is eigenvalue problem, yes? And what's the new eigenvector now? It's Bxi. So Bxi now, this is the new eigenvector now. So Bxi is eigenvector of A. So we assume that we have two matrices that are that can commute A and B, and now we knew that A has this matrix, this eigenvalue equation, so AXI equal to lambda XI. Then because the two matrices can commute, we reach to the fact that Bxi is the eigenvector of the matrix A with eigenvalues lambda I. So in this case, if xi are the eigenvectors of A and Bxi are the eigenvectors of A also, so in this case xi and Bxi are both eigenvectors of A, so that Bxi just will be equal to some constants lambda I multiplied by xi, because this is eigenvectors for A, yes, and those are the eigenvectors also for A, so they have to be correlated in some way or another. So we can write them Bxi equal to some constants or some eigenvalues here, lambda I, xi. And this is again what? An eigenvalue problem. So this is eigenvalue problem. So what this says? Xi is what? For this equation, xi is what? Is the eigenvector of B. Now, so we prove that what? Xi is eigenvector for A, and it is also eigenvector for what? For B. So xi is also, xi's are also eigenvectors for B. So now, when do two n by n matrices, normal matrices, A and B have the same eigenvectors? The first part is when they commute. We will have that. They will have the same eigenvectors. Of course, if you revert A and B, the eigenvectors of B are also the eigenvector of A. If you do it the vice versa, revert both together. Now, the second part here, suppose that A and B now they will have the same eigenvectors. So the first part, we stated that in order for them to have A and B to have the same eigenvectors, they have to commute. We want to prove the reverse. If they have the same eigenvectors, should they commute or not? And this is what we are looking for right now. So A and B have same eigenvectors, let's say, in common. So A can be written as AXI equal to lambda I xi, and because they have the same eigenvectors, I can write Bxi equal to mu I xi. So the eigenvectors are the same, but the eigenvalues are different. So these vectors xi will form a basis for the n-dimensional space. So we can write a vector x, for example, as a linear combination of ci xi. So the eigenvectors of both matrices A and B, normal matrices, will form a basis for the linear vector space. So I can write any vector in this linear vector space as a linear combination of those base vectors. So xi form a basis vector. We stated last time that if you have a normal matrices, you can get a set of what? Orthogonal bases. And this will be what? You will obtain a number of orthogonal bases if what? If the eigenvalues are distinct. If the eigenvalues are not distinct and they have some degeneracy, we stated last time that what's the rule? Gram-Schmidt can transform some of those non-orthogonal eigenvectors to orthogonal eigenvectors, and again we can obtain n orthogonal eigenvectors. So now we can write it as this, and then we can do the following. We can do A, B applied on X will be just A, B, and X. Vector X, the new vector X is just Ci Xi. So in principle, I can say that this is A, and then this is Ci Xi. But what's B? Is mu I what? Ci mu I x what? Xi. And again, I can write this as Ci mu I lambda I Xi. So this is this part here. So, and if I reverse it, I can write this as B A, and this is Ci Xi, and again I can write it as B Ci lambda I Xi, and then I will rewrite it again as Ci lambda I Ui Xi. So this part here is exactly the same like this part here. So those two parts should be equal. So AB x equal to BAX. What does it mean? A and B what? Commute. So what did we get out of this? If they have the same eigenvectors, they should what? They should commute. So if you have a normal 2n by n normal matrices, and you want to know when you will have the eigenvectors, or they will share the same eigenvectors, all what you will do is check if they can commute or not. So if they can commute, you will know that, okay, those two matrices A and B will share the same eigenvectors. Okay, guys? Now, let's look to another topic also in the same chapter. And this topic is about similarity transformation. Similarity transformation. So let's assume that we have a set of bases in the linear vector space. Those bases are EI. Bases in the linear vector space. So I can, in principle, write any vector x in terms of those bases as I equal 1 to n, and those are the component xi in the direction of those bases. So it will be x1, e1, x2, e2, x3, x3, and so on. If you remember the case for three-dimensional vector space, we used to write this as what? x1, I, plus x2j plus x3k, for example. Now, we want to know how we can transform a vector from a set of bases to another different set of bases. So let's assume that we will have another set of bases, but those bases, we will call them EI prime. And the relation between the primed and the unprimed bases can be given by A primed j is equal to the summation from I equal to 1 to n s ij ei. So what do you think what Sij should be? What do you think? Let's talk about, let's say, x, y, z. This is I, j, k, and I have vector x, let's say. Then I can have another x prime, y prime, z prime. In this case, I will have what? I prime, j prime, and k prime. So what will be aj prime and ei prime? This is just in 3 dimension. Ei primes will be what? ijk. And ej prime will be I prime, j prime, k prime. What do you think the matrix here is Ij? Will be the transformation matrix that will transform from ijk to I prime, j prime, k prime. Last time, the matrix transformation matrix was what? A rotation matrix. If you remember a couple of lectures ago, the transformation matrix has what? Cosine alpha or theta and cosine beta, alpha, beta, and it has zeros because we did not have any rotation in the z direction. But let's say we rotate in 3 space, it will be cosine alpha and cosine beta and cosine gamma. And what's the cosines? When you have cosine for a vector with another vector. So this is the projection, yes, the projection of vectors. Which vectors? On Aij. So that's it. So when you move from one coordinate to the other coordinate, the new set of bases, this transformation is just, you said that Sij is nothing more than the i's component. Sij is nothing more than the ith component of Ej prime with respect to the unprimed bases. So Sij will be the projection of Aj primed with the 3 components or 5 components or 10 components or n components, in this case, from the unprimed here. Okay, guys? And let's say that we have E1 has 1 and 0, and E2 is 0 and 1, and let's say E1 prime now, so this is a vector in 2-dimensional space, and it has 1 in the x1 and 0 in the x2, 0 in the x2 and 1 in the x, 0 in x1 and 1 in x2. Then the new transformation E1 prime is 2 and 4, and the other one E2 prime is nothing more than 3 and 1. To do this, so E1 prime will be just 2 E1 plus 4 E2, and E2 prime will be 3 E1 plus E2. So this is what? S11, and this is S21, and this is S12, and the one here is S22. This is just a simple manipulation. So now, why we are going through all this? Just we want to know how to transform our vectors or base vectors from one coordinate to the other, or one set of bases to the other. Okay, guys? So now we want to know how to transform those vector eigenvectors from one basis, set of bases, to another set of bases. So for any vector x, we can represent this vector x as xi components in the ei direction. Same vector, the same vector, I can write it with respect to the xj component in the aj primed. So a vector, I can write it as a component in what? ijk in 3-dimensional space, and I can write the same vector but with respect to I prime and j prime and k prime. So this is with respect to the unprimed set of basis vectors, and this is with respect to the prime set of basis vector. It is the same vector. It does not change. So if you look here, this vector does not change by the rotation of the coordinates with respect to the coordinates x, y, z, or x prime, y prime, z prime is still the same vector. It does not change. And when you, from the transformation matrix, it was what? Orthogonal matrix. And when you, from orthogonal matrix, when you do a rotation or transformation, you keep the norm of the vector. So the amplitude of the vector does not change, if you remember. Okay, guys? So the vector is still the same. So xj, ej. So we can write this as over I here, sorry, over j. I can rewrite it as over j, xj. And what's ej prime? So I can write this as what? Sij E I, and this is over what? Over I. So you can rewrite this again by rearranging, and this will give you EI over I, and this is J, and this is Sij, and this is Xj. I can rewrite it like this. So what's this, guys? E Xj prime. This is Xj prime. Yes? So what does it mean? What does it mean? X, the vector X equal to, now, summation of from I, and this is equal to what? Means that the components here, this component, look at this, X equal to Xi multiplied by the basis EI in the unprimed domain. Now, the same EI is multiplied by what? By this. So this should be equal to what? Should be equal to what? Xi. So Xi should be equal to what? And this is primed. Sorry, I made a mistake here. This is primed. This is EI, and this is Xj. So this is primed here, and EJ, this is X prime, and this is this one. Yeah, so everything here is the same. So this should be equal to Xi. So what does it mean now? What does it mean? So we have those two equations. It means that if we have a vector in linear dimensional vector space, and we want to transform the vector, yes? This vector, we want to transform the vector. We will notice that the vector transformation, here are the vector's components in the unprimed space. Let's say IJK in three-dimensional space. This is the transformation matrix that transforms the components from the primed space to the unprimed space. Did you see this one? Did you see this one? So I can write this one as X equal to a transformation matrix multiplied by X prime. I can write it like this. Here, what's this? I can write this as the component, the basis of the component, AJ prime. I can write them as S multiplied by E. So we'll make it like this in matrix form. So the components of the unprimed linear vector space will be transformed to the primed linear vector space with this transformation matrix. But these are the bases. How to transform the bases. And this is how to transform what? How to transform the vector components. Because those are components, this is matrix. So this is matrix, X matrix. I just put here. This is matrix. And X as a matrix is just X1, X2 up to Xn. So this is in matrix form. This is in vector form. So now, the component of the vector X prime can be transformed using this matrix, while the bases will be transformed oppositely. And what does it mean? So vector X is what? remind you is vector x. What's vector x? xi, ai, and it's equal to what? xg, ag. Yes? So now, if I want to transform ei, I will have what matrix? S. Here, if I want to make it the same, x prime will be equal to what? You will just take the inverse. So x prime equal to this. So let's write it here. E prime is equal to S multiplied by E, and x prime equal to minus S minus 1 multiplied by x. What does it mean here? That when you want to transform from a set of linear bases in the unprimed space to the primed space, you will use the transformation matrix X, S. But when you try to transform the components of the vector, you will use the inverse of this S. Now, if you want to get the vector itself, not the components, the vector itself, not the components, those are the components. If you want to get the vector itself, you will notice that you will transform this from the unprimed to the primed, and you will transform the component from the unprimed to the primed, so that you will have S and S minus 1 will cancel each other, and you will have the vector is the same in the primed and in unprimed spaces. Did you understand? So the fact that you have the bases will transform with the transformation matrix S, and the components will transform with the inverse of the transformation matrix S, indicate that you will have your vector unchanged. So the vector x is unchanged under transformation from space unprimed or unprimed space to primed space. And this is what I showed you. I told you that if you have a vector, let's say in three-dimensional vector space, and this is the vector x, now you will have x1 component here, x1, let's say x2, and x3. Those are the components. And you have I, j, k. Now, let's say we will have another set of base vectors and coordinates. Now I will have x1 prime, I will have x2 prime, I will have x3 prime, and also I will have what? I prime, j prime, k prime. So E prime will be equal to S multiplied by E, and x primed, the component, xi prime would be S minus 1 xi, where I is ijk. So I is ijk. But the vector x itself will be the same here. Okay, guys? So the transformation matrix for the bases is S, while the transformation matrix for the components is S prime, so that when you will compose the vector, and the vector is what? The components multiplied by the bases. In this case, the vector will not change between the two bases. Did you understand? So this is just, we try to show how we will do a transformation between one set of bases to another set of bases, and we will reach to what we call, in a minute here, I will show you what we call by similarity transformation. So this is just for vectors. So we showed that how to transform from the linear set of linear bases, for example, in the primed and unprimed spaces. Now, what happens if, for example, we want to transform an operator? So transformation, instead of vector, transformation of linear operators. So again, if you remember, x prime is just s minus 1 x, and x is just s x prime. Just remember those two. So now, let's assume that we have an operator A, like a matrix. Operator A. Matrix is operator. When you operate over a vector, you transform this vector to another new vector, for example, so matrix A. Now, let's assume that we have an equation. This equation, operator equation, says that y equal to A multiplied by x. And now, we want to see how we can transform this operator here. So y equal to ax, and y prime is equal to a x prime in the primed domain here. Y prime equal to a x prime. So I can use this y here to transform it from the primed to unprimed to the primed. How you will do this? If you will have y like here, x here. If you want to transform it from the primed, let's say, to the unprimed, you will use this S here. So what you will do is just you will say the matrix S, the transformation matrix. So S applied over y prime is nothing more than what? Y. Yes, from here. S y prime is y. So I can write y as S y prime. And this is equal to A, and what's x? S x prime. So if you invert this, what you will get? If you will multiply by S minus 1, the inverse transformation matrix in both sides, what you will get? Come on, guys. If I multiply both sides by S minus 1, so y prime is equal to what? S minus 1 A S x prime. This what we call similarity transformation. Similarity transformation operator. So y prime equal to this multiplied by x prime. So S minus 1A S is, we'll call it similarity transformation. And those similarity transformations are usually useful to transform the matrix A to a simple form. And this is what we will be seeing here. What are some properties of those similarity transformations. So if we have an n by n matrix B, it will be similar to n by n matrix A if the matrix B can be written as S minus 1 A S. So let's look at the first property. If the matrix A is equal to the identity matrix, what's the matrix B? B equal to what? S minus 1, what? I, S. What's IS? S. So this would be S minus 1, S. What's S minus 1 S? I. So matrix B is equal to matrix A. Yes? Similarity. So this is the similarity transformation. Okay? So the first property, if you have a matrix A, I, the identity matrix, try to do this and you will notice that B also is equal to what? Is equal to A. What else as properties? If we have A and B, they will have, if they are similar, if A and B are similar, they will have the determinant of A equal to the determinant of B. How to do it? Proof. The determinant of B is equal to, what's B? S minus 1A S. And this is the determinant. So from the properties of determinants, I can write this as what? S minus 1. And this is what? A. And this is what? S. What's the determinant of any matrix? Is a number. Yes? So I can switch order without any problem. Yes, guys? So I can make this what? Okay? Okay, guys? And from the properties also, I can write this as the A S minus 1 S. What's this? Identity matrix. So I can write this as A identity matrix I. What's the determinant of the identity matrix? 1. So in this case, I prove that what? If we have two similar matrices, the determinants of those two similar matrices should be what? Same. Okay, guys? And the matrix B, you just compose it of what? S minus 1 A S. By the way, guys, A, do not be confused, and you will say, oh, if B and A are similar, this means that A is exactly the same like B. No. Did you understand? No, they are not identical. You cannot say if A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, so B, because they are similar, is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is not true. It's only true for when A and B are the identity matrices. Did you understand? Now, third one is if you have A and B, the eigenvalues for A and B will be, if they are similar, the eigenvalues will be the same. So if A and B are similar, they have same eigenvalues. How to prove it? What's the eigenvalue for B? The characteristic equation, B minus lambda I. And this is equal to what? 0. So I can write this as what? What's B? S minus 1A S minus lambda I equal to what? 0. Okay, then I can write this as S minus 1 A S minus lambda. Here I can write this as what? Yes? I can write S minus 1 I S, yes? Because you do not introduce anything here for the identity matrix. Then I can take this again, and I can rewrite it as S minus 1 here and S minus 1 here. So it will be S minus 1 multiplied by what? Multiplied by A minus lambda I multiplied by what? S is equal to 0. And when you will have it like this, then this is the determinant. Now you can return back to the properties of determinant, and this will be the determinant of S minus 1, the determinant of A minus lambda I, multiplied by what? The determinant of S equal to 0. You can combine those together, and this will give you A minus lambda I, multiplied by the determinant of S minus 1, multiplied by the determinant of S, and this will give you what? And this is I. This is 0. Then the determinant of I is equal to what? 1. So what did we got here? We proved that what? They have same eigen values if they are similar matrices. Okay guys, I will stop here, and next time I will continue the properties and also will discuss the diagonalization of matrix, how we will do the diagonalization. Okay guys, do you have any questions? Okay, thank you so much.